Okay, so welcome in everybody. We'll get started in about a minute so that people have a little bit more time to sign on. I have some names in the chat that still say that they're connecting. In the meantime, if you are already listening, then that means you can definitely get started on item 1. Item 1, I need you to finish yesterday's triangle that we left off with at the end of notes. And the reason why I'm asking you guys to do this is that one of the most important things to take away from the law of cosines as a method or a technique is that it is probably our most complicated technique that we're ever going to learn this entire school year. But on any given question, you never have to use it more than once. This is due to the simple fact that based on the information that it produces, it kind of situates you in a good way to then use easier techniques to finish the question. So just as a quick recap from the end of notes yesterday, we were given a triangle ABC, which itself has 3 side lengths, right? We were given a side question, ABC. And those 3 side lengths were C is equal to 18, 10 is equal to A, and B is equal to 23. And so what I would like you to do is, based on the law of cosines work we did yesterday, well, that gave us an angle, right? So from yesterday, we used the law of cosines. And for more information on that, you could check your notes or you could check YouTube. And which angle did we solve for yesterday, kids?
Angle B?
Yeah, law of cosines gave us that angle B is equal to what?
It gave us 106.96.
Thank you very much. Perfect. Yeah, we got 106.96 degrees, which is a rounded value, but that's right here. So now that we have that angle B is 106.96 from the law of cosines, what does that give us? What do we consider these two numbers to form?
Wait, what 2 numbers?
They're going to be opposite angle pairs.
These two form an opposite angle pair. So now to get another angle, you can use the law of sines. And then once you have 2 angles, getting the third angle is really easy, I hope. After that, we have another law of cosines question, except this one takes a word question and has some context. So first I'll read it to you. And this one I might move out of the frame, but I think it's fair because you guys have the numbers, right? You guys have these numbers?
Yeah.
Okay. The second one, I wanted to be more interesting and have some context. So an astronaut on Mars observes an angle between the Earth and the Sun of 37 degrees. This is to say that an astronaut looks up at the, oh heck, I guess it's actually a law of sines question. That's fine, I guess this one's a little bit too easy, but today we'll do notes on a law of cosines question. Anyway. An astronaut on Mars observes an angle between the Earth and the Sun of 37 degrees. That is to say that if you were to go outside and look at the Earth and look at the Sun and point a finger at each one, then the angle made between your arms is 37 degrees. At what angle would somebody on Earth, right? So now if you're on Earth and you look up at the sky and you look at the Sun and you look at Mars, what angle do they view both of these celestial objects at? This information is calculable, which I think is really interesting. Of course, as a physicist, I care a lot about astronomy and the movement of the planets. And so to do this, we'll need some distances. And these are the same distances in a warm-up question that we had. I think it was a warm-up question from so long ago, we were still in class, where I talked about the distance between stars and planets, right? And these are true numbers. So the distance from the Sun to the Earth is 8 LM, which is the unit light minutes. It's a measurement of distance. And then the distance from the Sun to Mars is also in this same unit of light minutes. Does anybody remember what a light minute is? Anybody want to take a crack at explaining exactly how long that is?
It's how long light travels in a minute's worth of time.
It is how far a beam of light would travel if you gave it 60 seconds to travel. And that is an immense distance because light is the fastest thing in the entire universe. It is allowing the fastest object in the universe to travel for 60 seconds and then measuring the distance that it traveled with a meter stick. Wild stuff. So let me fill out some context here with this. So I like this question, and I call it the pale blue dot question, because a very famous scientist named Carl Sagan kind of took one of the most famous photos of all time. And I don't mean that he took it like he was holding a camera, but let me show you the pale blue dot. Do y'all see that image that I'm sharing now?
Yeah.
And please, if you know the answer for sure, don't say anything, because if you know this, you know this. But those of you who haven't seen this image before, who haven't heard of this image before, what do you think this might be?
The atmosphere?
Of what?
Our Earth. Our Earth.
Is it
Yeah.
a photon?
Is it what?
A photon?
That's basically what it appears to be, where a photon is technically a particle of light. So all images are actually photons bombarding into your eye holes, right? So technically, yes, this is the observation of many photons actually to form an image, at least billions. But the image, the pale blue dot, is a picture of the Earth. This blue dot right here, that's the Earth.
From how far?
Really?
That is the correct question. That is the next question you should ask. You should ask from how far. This picture was taken from Saturn. Now, the way that we got a camera all the way out there was we have this wild satellite called Voyager. And so now I believe I'm sharing the scale of the universe, which is a thing that I like to use a lot. You guys see that?
Yeah, you are.
Yeah. So starting off at the human size scale from 1 meter, to talk about these distances that we were talking about to produce this pale blue dot image, we have to at least get up to the sides of planets and whatnot, right? We have to get out of here. And so we're now at the Earth size scale. But what we're actually talking about in this question, number 2, are distances on the scale of the solar system. So to get out to a distance where it makes sense, here we're at the distance from the Earth to the sun. This is the distance that I'm talking about when I talk about 8 light minutes. At this size scale, light takes 8 minutes to travel from the sun, tick, 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 to the Earth. So since we've started lecture, it's been about 8 minutes. At the moment that we started lecture, a photon left the sun and it just hit the Earth. Think about it. Think really hard about it, okay? And then we pull back, further back, to the Kuiper Belt, and to, oops, sorry, we came out too far then. I must have missed the solar system. You know, I guess this is the closest one, out to the asteroid belt. So effectively, that picture for the pale blue dot is a picture of the Earth from outside of here. Like, you can see Mars from the Earth with the naked eye. If you look up at the night sky on a clear night and you find a bright red dot that doesn't twinkle, that's the main difference between planets and stars. Starlight twinkles, but planet light comes in a nice consistent color with no blinking whatsoever. So if you look up at the night sky on a clear night and you see a solid red dot that has no twinkle to it whatsoever, that red dot is Mars. Vice
Mr.
versa.
Robinson, you like froze for like a good half minute.
Oh, that sucks. Where did I leave off at? I guess my internet's bad.
I don't know, it might be mine. But...
Oh, did anybody else hear lag or delay?
No, I heard you. Fine.
Yeah. Yeah, you were good.
Oh, okay. Must have been local on Maria's end. But yeah, so the same way how like other planets in the night sky to us are little specks of light, our planet is just a speck of light from any reasonable, context. It's important to keep in mind that that little speck of light, that's here, right? That's the planet that we live on. That's home. That's us. On that little speck of light is everyone you love, everyone you know, everyone you've ever heard of, every human being who ever was or whoever lived their lives. The aggregate of all human joy and suffering and thousands of individual hunters and gatherers and foragers and heroes and cowards, and every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father and child and inventor and explorer, they all lived there on
Isn't
that
this
little
also
dot.
the picture in Pasadena too, the Caltech and JPL?
I mean, this is where it was received. So the image was taken by a satellite that was leaving the solar system from the perspective of Saturn. And then that photograph is turned into an email, basically, and then emailed back to Earth, where it was received and analyzed at JPL. But this image was taken back in the 70s.
Oh.
Yeah, this is just like the latest high-res retouching of it so that it's nice and clean. Okay, nonetheless, fun stuff. I just wanted a question that had a little bit of context. So let's go ahead and draw the functional diagram that will allow us to answer the question. If one person is on Mars and they see the Earth and the Sun at 73 degrees apart in the sky, what does that look like on Earth at the same time? How far apart would Mars and the Sun be? Are there any questions out there before I draw this?
There's a random question.
Yes?
I have a
Who's first?
random question about is there? I heard about this thing that there's a hornet, like a giant hornet that came to America from Asia.
The giant hornet.
Yeah, so when you have ecology on an island, you get all sorts of weird stuff. And in the case of Japan, Japan has giant insects, if you don't know.
Yeah.
Not just hornets or whatever, but also their spiders are nightmares, their beetles are nightmares. I don't like bugs to begin with, but whenever you have an island, you have weird animals and insects. And it seems like one of their bees has made it to America because we live in a world with global supply chains. So all it takes is one queen larva to accidentally hitch a ride in a box of produce or in a package or whatever. And then for that one larva to survive into adulthood, for it to start a whole new hive here. And I think it's in Washington. And yeah, that sucks. I hope they deal with that before it spreads down the West Coast because
that would be so bad. And they eat bees, and if they sting you, you die.
There's a good chance.
Both of those are hyperbolic. Yes, you can die if they swarm you and you get stung a bunch. And the destruction of bee colonies is already bad because bees have been in decline in the United States for the past 10 years, and they just recently started to recover. And if you don't know, they are the primary pollinator in our ecosystem, so no bees means no food. If bees go extinct, the ones that we use for our food supply, it's like a matter of 1 or 2 years before we do too.
Yeah.
Any other questions out there before I draw this diagram? Yes?
Wait, so when you were looking at the scale of the universe, the Minecraft world was on there. How do you actually get the
Oh yeah.
Yeah, I saw that.
Yeah, all that's about is that is if you took a Minecraft server and you expanded it to its maximum size by effectively having 4 people start at the spawn position, because that's 0, 0, 0, and then you have them walk out in 4 separate directions, generating the map as you go outwards. That is the maximum size that it could generate when all 4 people were to hit the edge of the world.
Wait, there's an actual edge?
There is an actual edge, but if you were to walk there in terms of human time, I think it's something ridiculous. It would take more than a year of now I'm not saying 8-hour days. I mean, if you tape down W on your keyboard and you just let them walk, it would take 400 days to reach the edge of the world. You can get there by hacking or whatever.
How do they calculate that then?
Just based on the memory that the game can access. All of your software, it has some maximum amount of RAM that it can access before the math that makes the game work stops functioning. The maximum size is calculated based on how much RAM Minecraft can access simultaneously.
Oh, okay.
Anyway, so this red dot is the sun, and of course none of this is to scale. If it was, the sun would be would have to be pretty big here, and then of course Mars would be such a small dot that I couldn't actually draw it on my diagram at all. But if this is sun and this is Mars, that means that this length from here to here is necessarily 11 light minutes. And then what I'm saying is, if you are standing on Mars, you're standing here on Mars, which allows you to see the sun and the Earth at the same time. You look up at the night sky, or I guess the daytime sky, and you see that from where you see the sun to where you see the Earth, that is spanned by about 37 degrees. So the Earth is way out here along this line, probably about there. And the Earth is a pale blue dot, so I drew it with blue ink, and I will draw its line in blue ink as well. And of course, this distance from there to there, that has to be 8 light minutes. So what you are being told here is that when you view the Earth, the spanning angle right here is 37 degrees. And so we are looking for this right here. If you are on Earth looking at the sky and you see the sun and you see Mars, what angle do you see between them? This number can be gotten from the information provided. I hope that's okay. Let's go ahead and do item 1 since we've had a lot of time to meditate on this. So like I said yesterday, we used the law of cosines to solve first for B. And then once we have angle B, we now have a side angle pair. So we can move on and we can actually solve for either angle. Which angle would you like to solve for first?
B.
We already have B.
Oh, C.
Let's go ahead and get angle C. So what we're going to do here is we're going to say sine C over C is equal to, and we have to set it equal to our other side angle pair, that pair being B and B, sine B over B. Now I need to isolate angle C here. So how do I get angle C alone? I need to do some algebra to get angle C all alone.
Oh, you multiply by.
Inverse sine?
Oh yeah, no.
We cannot inverse sine yet. We can only inverse sine once sine C is all alone. How do I get sine C alone?
I'd say cross multiply first, and then it's going to be easier to like figure
First,
out
I'm
what
going
to
to
do.
multiply both sides by C. Multiply both sides by C. On the left-hand side, C and C cancel. Now I arrive at the statement sine of C is equal to C sine B divided then by B. Now, how do I get angle C alone? I heard it out there as an answer to the previous step.
Inverse sine.
Now we hit it with inverse sine. So angle C is equal to inverse sine of C sine B, then divided by B. And now that we've solved for our desired variable, the rest is substitution. So this is going to be equal to inverse sine of length C, which is 18 sine. And we're going to use the angle B that we calculated yesterday, 106.96 degrees, then divided by side length B from the triangle, which in our case is 23. So angle C is equal to this thingy here that I get by feeding this to my calculator. And depending on your calculator, entering this might look a little bit different, but here are 2 ways that we can do it. If you're feeling fancy, you can put it all in at once. So that's me entering it all together, and this will give me my answer. For angle C here, I'm getting 48.47 degrees.
Yeah, I got the same thing.
Good. Or for a lot of y'all, entering this all together might be difficult. So here's another common way that you can enter it that a lot of people find a lot more natural. A lot of people will want to get the decimal that this ratio is on the inside first. So I can do that first. I can say 18 sine 106.96 divided by 23. So that's just going to give me whatever this wacky decimal is here on the inside. And then I need to do inverse sine with that. So I'm going to do second sine, and this is a true thing that a lot of your calculators have. Your calculator probably has a second answer button right here, or a second entry button right here. Basically what these do is they resummon the last line that you just put in, or the last answer. So what I'm going to do is I'm going to hit second, and then I'm going to hit this button because it has the word answer in blue. And what that does is it takes the answer from the previous line and it automatically enters it right here. So you could enter it all in at once, or you could do it in 2 steps, get the decimal on the inside, and then do second inverse sine of that answer, and it gives us the exact same thing, whichever one is more natural to you. And so first off with this question, yesterday we did law of cosines to get one of the angles. We got that this was 106.96. Now we know that angle C is 48.47. And then the final step to get angle A is what? That's the hard part, right? The hardest part of all of these calculations. How do we get angle A?
Very difficult. You have to do third angle theorem.
Angle A is then obtained by the third angle theorem. So all of these angles add up to 180, and now we have the other two. So we add them up and subtract them from 180. And you know, keep in mind that it won't be exactly the same for everybody because of rounding errors. Depending on how many decimals you round it to, it can affect your answer, or depending on which one you get first and then round, that can also affect your answer. You would get a slightly different answer here if you solved for B before C or C before B, etc., etc. But no matter what, it should be in the ballpark, and we should be getting out there that angle A is equal to 24.57 degrees. Is that okay?
Yeah, so for the law of cosine and sine, it's just like a formula and you like do it and then plug it in.
I would argue the same is true of SOHCAHTOA and the Pythagorean theorem. They're all just formulas, and you need to know where they apply, and once you identify where they apply, the rest is correctly using them. The law of sines and the law of cosines are just extra rules that we need because those first set of rules, they only apply to right triangles, but the law of sines, the law of cosines, they apply everywhere. They're harder to use, but they're universal. Okay, so here we want to solve for this mystery angle, right? The Earth angle, let's call it. So I'll go ahead and call this angle E. And so an astronaut on Mars looks up at the night sky and they see that the sun and the Earth are separated by 37 degrees. But this person on Mars wants to know, what do they look like from Earth? And so using these relationships, we can solve for this really quickly with the law of sines, yeah? So notice 37 and 8, that's an opposite side angle pair. 11 and angle E also constitutes a side angle pair. So here, sine of the angle viewed from Earth divided by 11 has to be equal to sine of 37 divided by 8. And so we'll solve for angle E quickly in one step. Angle E has to be equal to inverse sine of 11 sine 37, then divided by 8. It's the same manipulation as the last question, I just did it in one step. And then again, we can enter this into our calculator and get our final answer. What are y'all getting out there?
55.84.
Yep, 55.84 degrees. So while a Martian would look at the night sky and see that the sun and the Earth are 37 degrees apart, because of the lengths that we know about on the other side of that triangle, we know that an Earthling looking up at the night sky would see that Mars and the sun are separated by an angle of 55 degrees. Are there any questions on today's warm-up?
No.
Okay.
How did you know that it's like set up like that whenever you put like the original sine E over 11? Like, how do you know that it's set up like that?
The pieces that you pair off in the ratio for the law of sines, and this is also what tells us that we can use it in the first place, is they are opposite side angle pairs. So I know that 11 and E go together because they're on perfectly opposite sides of the triangle. And I know that 37 and 8 go together because they're on perfectly opposite sides of the triangle. And if we were asked to go crazy and finish this question, we could do it, because now that we have two of these angles, we could also get the angle that you would be viewing both planets at from the sun, which would also then let us calculate the distance from Mars to Earth. So these three numbers are actually enough to finish the entire problem, but I only asked for one of the angles.
Oh, okay. So this is law of sines.
Yes.
Oh.
Yeah. And so let me do the last example that we'll be doing together, and then tomorrow will be time to workshop. So real quick announcements just to make sure that we're all on the same page about what's happening this week. You guys have 2 homework assignments. One of them is due tomorrow. The other one is due Thursday night. Tomorrow is the only day that we have for workshop on this stuff, aside from any questions that I can answer for you guys today, because there's no class on Thursday, so I can take my exam. And then when we come in Friday, I'll start off with questions, and then we will have our chapter tests so that we can wrap the chapter up and put it away before you guys switch your concerns to AP tests. Now, this stuff is capable of being complicated. For the most part, I'm going to keep all of the requests about law of sines and law of cosines stuff straightforward. But to help you guys through it, I posted an extra homework. That second homework that I posted has the answers on the final page, so you can check to make sure that you are doing the work correctly as you move along. Now, keep in mind that if you just write down the answers for me, will that give you full credit on the homework? Will that matter? Do you get full credit for giving all the answers?
No.
No, you don't. And that's because you have to show all the work, which is actually where the credit comes from. So be sure to show all of your work. And if you need additional guidance when it comes to working on this stuff on your own, either today while you do your homework, tomorrow while you do your homework, or Thursday when we have no class, I also posted the links to the playlist on Khan Academy for Law of Sines and Law of Cosines, and they're really good resources. The videos are broken down into really small chunks. So one of them is straight up using law of cosines to solve for angles. One of them is using law of sines to solve for angles. One is using law of sines to solve for sides. So if you get stumped and you can't figure out how to do the manipulation, check out those links, find the appropriate video, and follow along at home. Today, we are going to look at the other kind of law of cosines question. Yesterday, we used the law of cosines. So yesterday, and we wrap this one up today, we use the law of cosines on an SSS question. And here were the steps that we did, right? We were given 3 sides of an oblique triangle, and we used the sides first to solve for an angle using the law of cosines. This is our recipe for those of y'all who just want to follow recipes to get correct answers. And then after we had that angle with the law of cosines, then we were able to solve for a second angle. And in the warm-up, what did we use to get the second angle?
Law of sines.
Then we use the law of sines to get the second angle. And once we have 2 of the angles, it's easy to get the third one. There's a theorem for it. It's called the third angle theorem. This is the solution procedure to basically every oblique triangle of the side-side-side variety. Step 1, solve for one of the angles using the law of cosines. Step 2, solve for the second angle using the law of sines. Step 3, you have 2 of the angles, get the third one by the third angle theorem. Today, what we are going to do is we are going to do the other kind of law of cosine question, and we are going to use the law of cosines on an SAS question. And just so that we all know what we're doing before we get ahead of ourselves, here's the recipe that we're going to follow today in order to complete this variety of question. Number 1, we are going to use the law of cosines to solve for the third side. We have 2 of the sides to start off with, and the law of cosines will let us quickly get that third side. After we use the law of cosines to get that third side, then we can solve for a missing angle using the law of sines. And then after we have 2 of the angles, once again, this problem is finished off by using the third angle theorem.
Mr. Robinson, even if you wanted to and you had an oblique triangle and you split it in half, you still couldn't solve it with Pythagorean theorem?
No, you couldn't. You would need more information than is being provided to actually go through the hassle of setting up the altitude. The altitudes are just an intermediary term that we use to invent these equations to show that they're true. But after it's canceled out in the algebra, it's also canceled out in our solution procedure.
Oh.
That's the way of math, dude. We have these simple rules. We use them to build big rules. We use those big rules to do crazy stuff. And at some point, you kind of forget where the rules came from. Like, I only know these proofs because I do them every year. But for the most part, you moving forward, you don't need to know that proof. You only need to know the equation and how to use it.
Oh.
That stuff, like where it came from, that's just enrichment in case some of y'all end up majoring in math. And it's also good to know in case you have to use bits and pieces of the equation in unique ways. So, for example, here is the other kind of law of cosine question that one could face. A question where we're given a side, an angle, and a side. So we'll start off by drawing a triangle here. And this triangle looks like this. And our triangle is going to be named A, B, C. And all that we actually know is that angle C here, I might as well just get the real angle, right? Working on paper, so I can use a real paper protractor. And that angle seems to be just over 60, about 63 degrees. So this right here is 63 degrees. And past that, the only other, I'm sorry, that's hard to read. Oh man, also, did I tell you guys yesterday my black ink dried out?
You did.
Yeah.
Oh, okay. We'll go ahead and say that BC here is a unit length of 12. And then AC here is a unit length of 11. And so based on this information, we are being asked to complete the triangle. And if we haven't talked about it before, just so you know, being asked to complete a triangle is being asked to give every number for it. So keep in mind always that a triangle has 6 parameters, 3 sides, 3 angles. How much information are we being given?
3 components of it.
We're being given 3 components right here, right?
Side.
And so we need to give back 3 as part of our answer. Our answer needs to include 1 side and 2 angles. So being asked to complete this triangle is actually being asked for angle A and angle B, and what other piece?
Side AB.
But what is the actual name of side AB?
Angle lowercase c.
Side length lowercase c, but
side
yes. And so the reason why I asked that is that keep in mind that the standard way this is written in here and in algebra and in pre-cal and in any math textbook for whatever reason is that if this is angle A, who is this?
Lowercase c.
And if this is B, who is this?
Lowercase b.
And that's important. That comes into play in terms of the nomenclature of how the law of cosines is written. Yes.
If they gave you a triangle and they gave you those same 2 sides, but they gave you the angle of angle B, could you not solve it?
You could solve it, but you would solve it using the law of sines. So if you are given an angle side pair, right? If you are given side B and angle B, then you just jump straight to law of sines, and it's a pretty easy question. But here, specifically in the case of SAS, we don't have an opposite sided angle pair. For A, I only have the side. For B, I only have the side. And for C, I only have the angle. So without a pair of letters, we have to revert to the law of cosines.
So it's only SAS whenever it's actually in the order side, angle, side?
Yes, the letters are not the total collection of variables. They are the order in which the variables are laid out around the triangle. These are all good questions. Okay, so like I said, I kind of gave you guys a procedure here because it's really hard to see what the strategy is that we would use here. But luckily, our recipe says, number 1, we're going to use the law of cosines to solve for a side. So the law of cosines version that we're going to pick is going to be the one where it's already equal to that side. It's just going to make our life that much easier. So c squared is equal to a squared plus b squared. What is that?
Pythagorean theorem.
It is the Pythagorean theorem, but it's also can be considered the incomplete law of cosines. Because all we do to make this into the law of cosines is we're going to subtract 2 times some stuff. What stuff do we subtract to transform it into the law of cosines?
Minus 2ab.
This one is going to be minus 2ab cosine.
Cosine c.
Very good. And you can either get that from your notes and just have it somewhere handy dandy and ready to go whenever you need it. Or we can recognize the pattern. These letters in the middle are the same, A and B, minus 2AB. this side length and this letter, those letters also match. So now we're solving for side length C. How do I get C alone? What do I have to do to get C alone? What
Square
operation
rooted?
is being done? Yeah, say that again.
Square rooted.
Yeah, notice here C is being squared. So if I want to undo that, all I have to do is hit both sides of this equation with a big square root. So this is to say that the square root of C squared, those guys will cancel, giving us just C. And on the right-hand side, the algebra says if I do it to the left, I do it to the right. This must be equal to the square root of a squared plus b squared minus 2ab cosine angle C. And so from here, the rest is plug and chug. So this is asking us to take the square root of a squared plus b squared minus 2ab, a b times cosine of angle C. Using the law of cosines to solve for a side length is a lot more straightforward than using it to solve for an angle. You literally just take the square root of both sides and then plug and chug the terms. And so I'm just going to enter this into my calculator all at once. Or you can do the thing I said before and enter it in two pieces. But nonetheless, I'll do it in two pieces. So it's going to be 12 squared plus 11 squared minus 2 times 11 times 12 times cosine 63. A whole bunch of stuff, but that's just me entering every single one of the instructions on the inside all at once. So that gives me a big number. 145.15. And now what do I have to do in order to get the final answer?
Find the square root of it.
Yeah, we have to take the square root of this. So I'll do second square root, second answer, because on a calculator that will automatically pull up the last digit that it spat out and plug it in for us so that we don't have to retype all that junk. And that tells us that side length C is equal to 12.05.
Do we have to do like approximately?
Yes, and that is true whenever it is rounded. So here, this answer is precise. This gets a full equal. This is only approximately equal because we rounded off all of the data from all of these decimals.
That's all it is?
What do you mean?
It seemed so much harder yesterday.
The one that we did yesterday, I started with the hard example. I always almost start with the hard example with these two. Using it to solve for the angle, you have to do some fancy manipulation, but the law is set up to actually quickly produce whatever this length is. So if this is c squared on the left, it'll quickly give you c by taking the square root. If it's a squared equals, it'll quickly give you a by taking a square root. If it's b squared equals, it will quickly give you b by taking a square root. Okay, so that's one bit of our puzzle. So up top in our puzzle here, we are trying to solve, we're trying to complete the triangle, that is, and we just got this one. C is equal to 12.05. Which angle would you like to solve for next?
A.
Okay, we'll solve for angle A, and here's what's going to make that possible. C and C now both form a side angle pair. I have that angle C is 63, and I have that length C is 12.05. Whenever that is the case, you may now use the law of sines. So that is to say, sine of A over A is equal to sine of C over C. Solve for angle A. A is going to be equal to the inverse sine of A sine C over C. This is the same manipulation as we did in the warm-up. It's one that you should get comfortable with. Multiply both sides by A, that gets sine A alone, and then hit this homie with an inverse sine to get A alone. And so we get the inverse sine of A sine C over C.
Which one of the C's is capital? Like, I can't tell.
The angle. It's always the one on the inside of the sign. This one down here is lowercase. And yeah, it's really hard to see with C. I should use letters that are evidently different, like D would be a better choice, ABD.
Yeah.
Nonetheless, you'll always see it as C in the textbooks, and it's a lot easier to see when it's printed. Nonetheless, this is going to be equal to the inverse sine of 12 sine 63 degrees, then divided by 12.05, which we just solved for. And so this is going to give us angle A very quickly. So that is to say inverse sine of 12 sine 63 divided by 12.05. And we get that the angle here, I believe, is 62.54 degrees. So angle B is 62.54 degrees.
Why do you set up that proportion whenever you're always going to get that second equation anyways?
Because that is the fundamental, that is the proven version of the equation. That's just like the way that we write it formally. This is just traditionally how we do math, that you always start with first principle, and then you show in a few steps how you manipulate that principle into a useful form. Again, it's just a thing you get used to, because like when I hand notes back and forth with the other grad students, this is the way that we all do it, and it makes it so that it's comprehensible to see what the person is trying to say with all their numbers.
Oh.
And so that gives us 2 of our 3 components, and luckily when it comes to these law of cosines questions, the last part is always nice and easy. Third angle theorem. So I have that one of my angles is 62.54, and I have that my other angle is 63. All of the angles in our triangle need to add up to 180, so I'll subtract their sum from the total, and that tells us that the last angle is 54.46 degrees. So, grand total summary for trigonometry. We are given 3 numbers, and depending on which 3 numbers we are given, we should be able to solve for the other 3 numbers present in that triangle. Now, one kind of information that's not useful, we can't do anything with 3 angles. At least one of the numbers that we need to be given must be a side length in order for us to actually do trig. And when it comes to doing trig, if you're being asked to complete a triangle or solve for some junk, I highly recommend this flow chart that we started yesterday, but I'll round it out today because I think this tells the whole story. So when you're asked to complete a triangle, right, the first thing you want to ask yourself is this thing a right triangle? Do we have at least one angle which is 90 degrees? Is that one of the 3 numbers I was given? The information that we have a 90-degree boy in there. If you do have a 90-degree angle, then we instantly switch over here to the yes side of this flow chart, and we have 2 tools in our toolbox which are amazing. SOHCAHTOA and the Pythagorean theorem. If you know how to set them up, if you know how to use them, this can be used to quickly complete any given right triangle. That's what we did on the quiz. Post-quiz content is how to deal with an oblique triangle, right? You ask yourself the question, is it a right triangle? No, because it's oblique. You then need to ask yourself a follow-up question. Do we have an opposite side or angle pair? If you have an opposite side angle pair, that is to say, side A and angle A, side B and angle B, or side C and angle C, if the answer to this pair question is, well, oh, yes, then we use the law of sines in order to solve the entire problem. Nice and easy. Law of sines being sine of A over A equals sine of B over B equals sine of C over lowercase c. And you set up one proportionality and you can cross multiply to solve for any of the missing terms. You can use this to get, you plug in 3 numbers and you solve for the 4th one. However, for the law of cosines, if we don't have a side angle pair, there are 2 different kinds of questions that can fall under this subcategory. The 2 different kinds of questions that can fall down here are it's either SSS or it's SAS. And for the solution of these 2 types of questions based on how they're given, if it's SSS, the first thing that we want to do is we use the law of cosines to get an angle. You never have to do the law of cosines more than once, because once you've done that, you can then switch to the law of sines. And then after you use the law of sines to get the second angle, you have one angle, you have a second angle, now you can get the third angle by the third angle theorem. Or if it's an SAS type question, like the example we just did, we start off by using the law of cosines to get a side. Once we get that first side, it provides us with a pair that then allows us to use the law of sines. And once we have obtained our second angle, we can then again finish this question off with the third angle theorem. Literally every single question on the chapter test can be answered by this flowchart. You're given some sort of triangle and asked to do trigonometry with it. Is it a right triangle? If it is, we're probably in the first half of the test and we're nice and happy because the combination of these 2 fancy skills will let us finish the triangle. If we're in the second half of the test and we're asked to complete a triangle and it's not a right triangle, We switch off to the right-hand side. Then we're asking, do we have a side angle pair? If we have a side angle pair, law of sines. If we don't have a side angle pair, if it's either SSS data or SAS data, then we're doing one of our law of cosines routines. Friday's chapter test, just so you know, this is it. This is what is there. So in terms of content on Friday's test, the first half of it will be the same as the quiz. So the first half will include everything from the quiz. You'll be asked to use the Pythagorean theorem and do SOHCAHTOA. The only notes that I'm going to give you about this is I'm going to ask a little bit less questions about special right triangles. And no vocab. So that first question where I was like, hey, how do we derive the law, where does the Pythagorean theorem come from? And you had to answer it's based on areas, based on that puzzle we did. There won't be anything like that at the top half, so there's no use in reviewing your vocab. And the other stuff that I'll call out from the quiz are those questions on the back where I asked you guys to complete the triangles using a specific ratio. Those questions will be there again, and one of them will actually make a reappearance. So one of the questions, one triangle will make a cameo. That is to say, you know, look over your quiz, and if you know how all of that stuff works, then one of the questions on the test will be free, because one of the questions on the test will be the same as it was on the quiz. For the second half, I'm going to ask 2 questions about elevation and depression. Those are just regular old right triangle trigonometry. The only difference is we're putting them into some sort of word problem, right? So we're talking about the height of a tree, the height of a building. There's something down in a canyon. I like this one. You're in a hot air balloon and you're looking at some losers on the ground at an angle of depression. You can also do some pretty good trig there. Any sort of one of those word questions from section 5. And then of course, the rest of this will then be oblique triangle trig. And here we're going to be looking at most likely 4 oblique triangles. And that'll be Friday's chapter test. I just want to get this stuff wrapped up and done and out of the way. Is this okay? Does this stuff make sense? Are there any questions? Oh, okay. Are there any questions out there about what we're doing tomorrow? Tomorrow's just workshop on the current live homework assignments. One is due tomorrow night, one is due Thursday, chapter test Friday. Are there any questions? We still have about 5 minutes. Are there any questions left on the homework itself? Did anybody start the law of sines or cosines homework and have a question ready to go?
I started, but I don't have a question.
Okay.
I finished.
Tight. Like I said, that second assignment has the answers, so you can use that to check your answers. Tomorrow when we're in class, I'll go over all of the answers to the worksheet that came with the textbook. I'll read them all out so that you can get them. Though, of course, you should know that for all of that stuff and for literally every single one of those questions, you know, there exists some kind of calculator in the world that will do it for you. So even like similar to our last question that we just did, if you were working on that question on your own and you wanted to be sure that you got it right, you could do that pretty easily. So for that triangle before, right, we were told that side length A was 12, side length B was 11, and angle B was 63 degrees, and we were given no other information, right? If you want to check your work, you can do that, and it is quick and easy, and it gives us, oh wait, heck, did I put something in wrong? Oh, I put the side in the wrong position. Right, because it's SAS, it's 11, 63, and then 12. Right, and check it out. It gives us the exact same answers that we just calculated. The other two sides are 12.04, and the other two angles get measured out as being the same, 62 and some change, 54 and some change. So this calculator is tight because it will help you check your answers. But will this help you on the test? Will this calculator get you full credit on the test? If I asked you that question and then you wrote the correct answers for me, you just were like, oh, these are the answers.
Nope.
No, why not?
Because we're not showing our work, so you can't. It's like you can't validate that we did it or not.
Precisely. If I don't see a law of cosines manipulation leading to that first angle, no credit. If I don't see a law of sines manipulation leading to the next angle, no credit. Just letting you know, stuff like this exists, and you can use it to do the homework. It won't help on the test. Make sure you can do all of these ops by hand. And anyway, that takes us to the end of the period. So if there are no further questions, you all feel free to pack up, head out, have a nice lunch. I don't know what they're serving today. And I will see you all on Wednesday, where we will get a chance to workshop the current assignments in order to prep for the test on Friday. Since there's no class on Thursday, before we start the test on Friday, I'll take last minute questions. We'll probably open it up for 5 or 10 minutes, depending on whatever y'all need. And then we'll spend as much time as is necessary to then take the test out. You all have a nice day, and I'll see you tomorrow.
See you.
See you.
Go do some trig, y'all. Trig it up.